Welcome everyone to the next, the second talk of the day. So we're very happy to have Madalena Lemos, who's going to tell us about the Regge trajectories and 2,0 theories. Please, Madalena.
Thanks, and thank you very much for the invitation to talk here. It's a shame we can't be in person again. So I'm going to tell you about a paper that came out recent with Walt and his student Chang. And yeah, please interrupt at any point if you have questions or if there's some issue with the sound or any other technical thing. So this is the rough outline of the talk. I will start by some quick introduction and the highlights of what we're aiming for. And then I'll go on to describe what we are uncovering as the structure of Regge trajectories in 6D n equals 2,0 CFTs. And then I'll give some very quick details on the inversion formula for 6D and also on an attempt to try to use the inversion formula to bootstrap the spectrum. And I'll give a little bootstrap in quotation marks to the spectrum. I'll give a little more details as we go along. So for this audience, I can be extremely brief in the background. Simon has showed us how the CFT data is analytic in spin, in the sense that if you're given a 4-point function, a correlator like this, you can write it as an integral over the principal series with some of blocks and then with some function C delta L that basically packages all the CFT data in the sense that C delta L has poles where your operators are.
So will the version be like this?
No.
Sorry, was there a question? I could hear.
No, it's okay, Madalena. Go ahead.
And that the residues are of this function. So this function has poles where the operators are, and the residues are proportional to OP coefficients. So Simon showed us how this function that packages nicely all the CFT data can be obtained through a Lorenz inversion formula. Oh, sorry, maybe just before going on, I can quickly say how this packages the CFT data. So this function has poles where the operators are, and here this integral I'm integrating in delta along this line, the half from along the half from minus I infinity to plus I infinity. Oh, sorry. And now it moved places. Sorry. Okay. So here we're integrating like this, and then you can see how you recover the normal OP decomposition you'd be familiar with just by deforming this contour here and picking up the poles along the real axis where the operators are. So this function that nicely packages all the CFT data, Simon has shown us it can be obtained through a Lorentzian inversion formula that I wrote schematically here. Lorentzian because we're integrating over Lorentzian kinematics, and it's basically the integral of some kernel function that I didn't write down explicitly, but that depends on delta and L, times the double discontinuity of the correlator we were studying, where the double discontinuity is comparing the correlator in its different continuations around the branch cut that starts at C equals 1. So you continue in different ways around this branch cut. And this formula is valid now for any arbitrary L. So it's valid, it gives an analytic continuation in L of this function that was only defined for integer L. And this formula is valid for as long as the real part of L is bigger than 1. So in this sense, is that we say that the CFT data can be analytically continued in L. And so we find the Regge trajectories, which are the analytically continued operator dimensions, which are the poles of this function. And as you've known and seen in many talks on the Bootstrap collaboration, this analyticity in spin has explained the success of the light cone Bootstrap, and also has explained the structure that is observed in the spectrum that's obtained numerically for various series, for example, for the 3D easing model. So my talk now is supersymmetric. And the idea is that supersymmetry is making our lives easier. So we are used with supersymmetry of being able to obtain exact results. There are operators with protected dimensions and sometimes even fixed OP coefficients. But what more relevant for this story is that supercharges also relate different spins. And so in particular for 2,0 series, the supercharges relate a spin with a spin plus 4. And so naively, this would get you to expect that you have analyticity to lower spins. This is just a naive argument. We'll do a little bit better. But naively, you would expect analyticity for spin bigger than -3, which now includes all relevant spins in your series. So now you can actually reach the whole CFT spectrum with the inversion formula. And now we have basically two rigid structures to impose in our theory. We had on one hand the supersymmetry that comes with its supersymmetric structure and all the protected stuff. But we also have the analyticity in spin that also implies operators organize in, so conformal families must organize in Regge trajectories. So what we tried to study here was the interplay between these two constraints. On one hand, supersymmetry that imposes relations between different conformal families. And then analyticity in L that tells you that all conformal families must somehow organize themselves in Regge trajectories that are analytic in spin. And this led to intricate connections between Regge trajectories of both protected and protected operators. So supersymmetry ended up demanding certain relations that constrain not only the protected spectrum, but also the unprotected Regge trajectories. So we'll see exactly how this comes about. And one highlight of the results is that we will see. So I claim that we'll have analyticity for spin bigger than -3, and we'll see how negative spins play a role. We will see that a long trajectory at spin equals -2 must give a protected trajectory that is none other than the trajectory of the stress tensor. So this extension to negative spins is not only, we're not exaggerating by saying L bigger than -3 and not just L bigger or equal than 0. We actually get something, some meaningful statements when we continue the trajectories down to negative spin. This is one feature of going to negative spin. Another consequence of L bigger than -3, where here actually L bigger or equal than 0 would have been enough, is that we can now attempt to do some iterative bootstrap of the theory. So let's say we start from an approximate spectrum. So from some knowledge of the spectrum. And in a supersymmetric theory, there's a natural candidate for this, which is just say, I know the protected operators. And now we invert. And we get everything out of this. So the protected operators are the ones with the lowest drift, meaning that we know that they're the dominant contribution for large spin. So at large spin, at least, we expect this to give a reasonable estimate for the spectrum. And then when we invert, we get everything out. And this is some sort of a corrected spectrum. That we can then plug back in and repeat. So this is a bit uncontrolled in the errors. We know that at large spin, the leading contributions do indeed come from the protected operators, but we're ignoring infinitely many Regge trajectories of larger twists subleading operators. But it's still something we can try, and we experimented a little bit, so I will show you the results at the end. So this was sort of the highlights of what we will be doing. And now I will introduce a little bit the target. So we are studying the maximum supersymmetric series in 6 dimensions, and 6 dimensions is also the maximum dimension where you can have a superconformal algebra. So for people who care about 6D n equals 2,0 series, we care about them because play this prominent role. Many lower dimensional series can be obtained from them, etc. And they are perfect candidates for using bootstrap approaches because we really have no other practical ways to describe them. They have no Lagrangian description. We know they have an ADE classification, so they are labeled by a simple and simply laced Lie algebra. And we know their central charges. And throughout this talk, I'll be referring to C as the 2-point function of the stress tensor. This is the central charge I'm talking about. We also know something about the protected spectrum of operators. In fact, we actually know infinitely many of the coefficients from the chiral algebra. So I will be calling this chiral algebra short operators. So this is an input we get to use. And we also look at this here numerically. So we have some numerical estimates. Whenever we play this iterative bootstrap game, we can compare with the numerical results and see how it works. And this theory was also studied in 1/c expansions by a variety of authors. And so we will also be able to compare our results at large C with these ones. But we will always work at fixed finite C. We can take it to be large, but it's always at fixed C. You will never be doing anything perturbative in C.
Madalena, can I ask a question just to clarify? So are these theories fully classified, or this classification is a conjecture?
I think it's
is it like
coming from string theory.
Is the situation the same as in n equals 4 in 4D? That we think there is only super Yang middles, but there is no bootstrap proof of that?
Yeah, I don't think there is a bootstrap proof of this. Here, maybe it's a little bit more. Well, the arguments are all in string theory, and that's how the classification comes about. So maybe it's a little bit more than n equals 4. In n equals 4, I'll say something differently. I would say that every n equals 4 theory has a conformal manifold, and then the question is if every conformal manifold has a weakly coupled point, so I can describe it with the gauge group.
I mean, the motivation for the question, is like if you can have basically, you know that the dual at large n is going to be ADS 7 cross S4, right? But you have all these Kaluza-Klein modes in the S4. And can you truncate to 0 modes and find some UV completion of a pure 7-dimensional supergravity? And I think at least in the analogous question in ADS 5, we don't really know the answer. So I was wondering if here we knew more, but I guess the situation should be similar, no?
As far as I know, it's similar. Yeah, maybe others. I don't know if Chris has anything to add, but I don't think it's in better shape.
Thank you.
I would just, I think from a bootstrapper's perspective, that's right. I think there's a bit of an argument based on sort of moduli space physics. If you assume a certain amount of yoga sort of dogma about how these theories should have moduli spaces that are tensor branches, there's some classification of sort of self-consistent low energy effective theories that leads to the ADE classification, but it's not, I mean, it's using a lot of technology which doesn't fit into the sort of conservative CFT approach.
Thank you.
So yes, then we do know a little bit, and as Chris was saying, since we know the moduli space, we know how it's described, we know that there are certain half VPS operators or even quarter VPS operators that this series must have from this type of arguments. And the chiral algebras were actually conjectured for this series of series. So in principle, we could use the chiral algebra to learn about these chiral algebra short operators. And in practice, this is what we will do for this, for the correlator we'll study today. So what we want to study is, again, emphasizing that it's really at finite C. We want to study the most universal multiplet first. So this is the multiplet that contains the stress tensor. And the superprimary of this multiplet is a scalar. It's a dimension 4 scalar that transforms in the 14 of the R-symmetry algebra of 2-0 series, which is SO5R. And this guy is related by supersymmetry to the stress tensor of the theory. Studying the 4-point function of this superprimary actually suffices to know everything. So if you know the 4-point function of this superprimary, you actually know the 4-point functions of all operators that fit in the same superconformal multiplet. So in particular, you'd be able to fix the 4-point functions of 4 stress tensors. And this was basically done in this paper some time ago. Because the guys we are studying transform non-trivially under SO5R. When you take the OP between two of them, you will have operators appearing in the tensor product of the representations that appear in the tensor product of the 214s. And this is the long list here. So then we have 6 channels, 6 R-symmetry channels that I'm calling capital A sub R. And each of these channels has a decomposition in conformal blocks with different conformal primaries being exchanged here. And these 6 R-symmetry channels are not completely unrelated. They are related by supersymmetry. And they are completely determined from 2 functions, one function of 2 variables and one function of 1 variable. So this function of 1 variable is, unsurprisingly, the chiral algebra correlator. And this is a full function of 2 variables that contains all the unprotected stuff inside. And this relation is through a differential operator, so there's some complication that comes from this. But in principle, or in practice, once you know these 2 functions, then you know all of these channels. So as I said, this H is related to the chiral algebra correlator, and it can be fully fixed. I just wrote it down here in full glory. So you see it's an explicitly known function where the only free parameter is the central charge, the 6-dimensional central charge, the 2-point function of the stress tensor. And from this, you can read off the OP coefficients of short or protected operators. And these are the guys I will be calling chiral algebra shorts throughout the talk. So from this, we can just read off an infinite number of OP coefficients. And then we have the other function, which is the one we're interested in studying in bootstrapping, that now receives different contributions. It gets contributions from the chiral algebra shorts. And these contributions we know because we just read it off from above. Then there are other shorts that are non-chiral algebra shorts. And these guys have fixed dimensions, but unknown OP coefficients. And finally, there are the long operators, which we know nothing about. So then delta and lambda squared are unknown. And so this function, this precorrelator, turns out to admit a decomposition in terms of blocks. But now we got some weird blocks here. We got a shift of 4 in the dimension, but we also got a shift in, so these are blocks for 4-point functions of unequal dimension scalars, where the dimension of difference between guy number 3, guy number 4 is -2. So even though we're considering the 4-point function of 4 identical scalars, all of the same dimension, for this function, we actually need to use blocks that have these shifts here. So these are, in essence, these are the super blocks.
Madalena, so this delta D plus 4L, are these Dolan-Osborne 6D blocks which turn out to play the role of super blocks, or are they something else?
Exactly. So what is a super block is this weird gadget. So as I had here, each of these symmetry channels is just a normal bosonic CFT, if you will. So it would be decomposed in 6-dimensional. So these are obviously 6D blocks, conformal blocks.
Mm-hmm.
And it turns out that now supersymmetry comes in and it tells you that, okay, there are relations between different of these OP coefficients when they come from conformal primaries that are related by supersymmetry.
Mm-hmm.
And you actually don't need to worry about these capital R's, about these capital ARs and the relations they impose, because these relations are completely given to you if you work out how if you work out the capital ARs from the tiny A's. So the tiny A's have a decomposition in blocks, and these are normal 6D conformal blocks here of Dolan and Osborne. Supersymmetry just the fact that it's a super block, it just means that it's what requires you to have this funny thing here.
Mm-hmm. Mm-hmm. Okay, thanks.
And so once you act with these differential operators on these tiny A's to get the capital A's, magically acting with the differential operators on these shifted blocks will give you just you can decompose that in a finite sum of conformal blocks.
Sounds good.
So in the end, the way I've presented this story, I'm telling you, okay, yes, there are 6 symmetry channels that you need to consider, but supersymmetry is so nice that in the end, you just need to worry about this function, tiny a of r, tiny a of CZ bar, that admits a decomposition in something I would like to call a super block, but they're just normal bosonic blocks with some shifts This is all supersymmetry requires you to do. And once you know this, you know everything, so you're done. And so this is the function we would like to study in Bootstrap. And this function receives different contributions. One contribution is protected from the chiral algebra. And then there are completely unprotected contributions, and also contributions of short operators with unknown coefficients. And now I will just claim this at this point, and I will just quickly flash the details later. But what we would like to do now is to write an inversion formula for this A. And this OP density is what I will be studying, the CFT data that contributes to A. And the claim is that the CFT data that contributes to A is actually analytic in spin for all spins starting at -3. So we will do this by writing an inversion formula for, again, some function C delta L that is written from the double discontinuity of A. So we will just follow Simon's derivation, except supersymmetry will allow us to have this for spins greater than -3. So now I'm just claiming it. I will argue in a little bit. But this means that the CFT data that contributes to A is actually analytic all the way. All operators that contribute here have to fit in Regge trajectories for all spins, not just for spins bigger than 1.
No, but how can you claim this? This is not known even without supersymmetry, because this formula is derived in a certain strip. Then you have to show that analytically continues. I think it's not known that these rigid trajectories are actually trajectories and not something more complicated like cuts, maybe beyond the leading rigid trajectory.
I was expecting this question from you in the beginning when I reviewed Simon's work. So yeah, that's completely true. So all the statements we can make is that we obtain this function C delta L, and this is, we go from the Euclidean inversion formula, which is valid for d equals d half, delta equals d half. And then all the statements we make are about C delta L. And then I'm assuming, as is often done, that poles are all there is. So at integer L, this function has poles. That's the Euclidean inversion formula. And now I'm assuming that as I continue, these poles just move in position. And so the analytic continuation is just that. But you're right that this is an assumption. I'm not going to be adding anything new to that.
Okay.
The only thing I'm adding is that, so with the usual caveats that should go, and that's why I kept saying in the sense of analytic in spin, in the sense of what was done by Simon. The only thing that changes for us is that supersymmetry makes the Lorenz inversion formula valid for L bigger than -3 instead of L bigger than 1. And now I will, as is often done, assume that this means that the non-analyticities of C are just poles, and that then I'm studying, so this function is a metamorphic function in delta, and it has poles, and I'm studying the location of the poles as a function of L. And these are smooth functions of L that I will be trying to plot. And the same for the residues. But I fully agree that this is an assumption that I am making at this point.
Okay.
And I will comment a little bit more on this L bigger than -3, because there are also some, as you know, from dropping the arcs, we need to worry about the light cone on the second sheet as well. And we don't have a good bound for the light cone on the second sheet. So even there, you'll be entitled to complain a bit later when I argue for this.
Okay.
Sorry, can I just ask a quick question? Maybe I misunderstood, but you made it sound like you'll have to sort of repeat Simon's derivation in some slightly different setup. So why is this? Why can't you just apply the standard inversion formula to A? Because it's already decomposed in terms of standard blocks.
It's pretty much that. So because that gets a little bit technical, I was saving it towards the end. But in essence, is that with some caveats. So there are a few things you should worry about. One is the arcs. When can you drop them? And this is where supersymmetry will come in. And the other modification is that we need to worry a little bit about single valuedness. But yeah, it's exactly just applying Simon's derivation to a function that has a decomposition in blocks.
Well, I'm asking, I'm just asking why you have to apply the derivation, not just the final formula.
Yes, we just apply the final formula and we just make sure that along the derivation, we can actually drop the arcs more.
Oh, okay. All right.
That's all that is, basically.
Okay, but the final formula is the same.
The final formula is exactly the same. Yeah.
All right.
Yeah.
All right. Thank you.
So now I spent this time to tell you that for this theory, all you need to know is this function tiny a. And once you know tiny a, you're done. You know the full correlator. And this tiny a, as we just said, it has a block decomposition, so Simon's formula applies. And you'll believe me that we expect the Simon's formula to apply for spin bigger than -3. So this means that all operators, then we expect them to lie on trajectories, on Regge trajectories. The chiral algebra shorts, which are these guys here, they kind of trivially lie on trajectories because their dimensions are just fixed from their spins. These are exact trajectories that are straight. They have delta equals L plus 8. And the OP coefficients are also known. And also the OP coefficients are a smooth function of L. So these guys are done and we're happy. Then there are these guys, which are other shorts that are not chiral algebra shorts. Again, by the nature of being short, they lie on straight trajectories, but their OP coefficients are unknown. And we, from the usual law of analyticity, we expect the OP coefficients to be some smooth function of L. And then there are long operators. This would be the leading long trajectory and then subleading longs here. That should also lie on trajectories and so on. These trajectories should start at spin 0 because we have analyticity for spin bigger than -3. And from here, it doesn't seem that we have much use for the negative spin bit. And it would also seem that we are done. But this is not completely the case. And it turns out that
is there anything special about these long trajectories that you, is this supposed to be schematic, or is this actually how these long trajectories will go? So, and what determines their position? Is there some light cone intuition here that guides you? How did you draw them?
This was completely random trajectory that I drew.
Okay, so this point there's no.
It's not completely random because I drew it from the spectrum we observe of one of the 60 series of Bootstrap. So that's the rough shape that I put in it, but I have no, you could make light cone arguments to see where they have to asymptote coming from the chiral algebra shorts and so on, but I just drew an arbitrary trajectory at this point.
Okay.
Okay. So then from here, there is still no significance for the negative spins. And now, as I said, all our symmetry channels are obtained from this. But it turns out that just having this structure here is not sufficient to guarantee that all of these ARs have the appropriate, the Regge trajectories are analytic in spin in the sense that we expect them to be. So then analyticity in spin of these functions is not guaranteed. And in fact, we will see that demanding it will give constraint on the spectrum. So it will further constrain the Regge trajectories I drew, and I will have to come back and complete this picture, taking into account those constraints. So for example, let me look at the R-symmetry singlet channel, and let me start drawing Regge trajectories there. And I'm drawing here again the long trajectories. So this is the leading long, and this is each long. So supersymmetry relates different conformal families. This is the leading long super conformal primary trajectory. And this single trajectory will induce different conformal primary trajectories. And these are conformal primary trajectories of SUSY descendant. All of these that I drew here. And in this R-symmetry channel, you will have to believe me that it follows that the fact that A of ZZ bar had analyticity for spin bigger than -3, this implies that this channel has analyticity as the usual behavior. So Regge trajectories, I only expect them to make sense for L bigger than 1. So I should be looking only at things above this dashed line here. And now there are also short trajectories that are not to be subleading with respect to the longs in this channel, so I did not draw them. This is a very simplified picture. I just drew this particular guy, that is a stress tensor, that is it sits here with a very low dimension. And so when we look at this plot, we immediately see two problems. One is that this long trajectory starts at spin 4. So analyticity in spin would have me think that I should be able to continue this to lower spins. And this guy is a descendant. It's a SUSY descendant. So I start with the delta, a conformal primary of dimension delta NL, that is a super primary. And it has a descendant of dimension delta plus 4, L plus 4. And this is the guy that we're looking at that starts, if the super primary has spin 0, the descendant starts at spin 4.
So, sorry, so just to clarify, what you mean that it starts at spin 4, you mean that the known local operators start at spin 4. But since you said that this trajectory for the function A goes to -3, this trajectory can actually be continued to -1. Sorry, to L equals 1.
Exactly. So this trajectory can be continued to L equals 1 because of the L. And in between, you would expect, so here, as you were saying, these are the light transforms of local operators. And in between, they would be light ray operators, yes.
I'm just trying to understand the statement that you said, that the long conformal primary trajectory starts at L equals 4. You mean that this is the known local operators on this plot, that they start
This
there?
Is yeah. So this is a conformal primary local operator, yes.
I see. So,
and
but it's still true that from your statement about A,
I should be able to continue this all the way down to 1. But you see that I intersect, so I guess the problem is that I intersect another integer, which is 2.
Yeah.
And I should figure out what happens at 2.
Yeah, I see. Thank you.
And you can already guess what I'm going to do, because the other problem is that this poor guy, the stress tensor, is alone. If it's an interacting sphere, there are no higher spin conserved currents. So this guy just sits on its own. And so a natural resolution of this would be to just connect the two and to say that the long trajectory should go through spin -2. And then, yeah, of course, it continues, but it captures another local operator as spin 2.
Sorry, Madalena, I have a question about this. So was this plot for the singlet R symmetry operators?
Yes.
I see. Okay. I thought you said R equals 1 or.
Oh, sorry, this was the bold-faced one. I'm sorry. I mean, it's like the singlet representation.
Okay, thank you.
Okay, so then there is a natural resolution to this, which is that we say that the leading long trajectory should be continued down to L equals -2. And then it should capture the stress tensor and show it should have this, such that if this is a super primary trajectory at spin -2, it has dimension 2. There's a descendant that at spin -2 has spin 2. That's the stress tensor, and it has dimension 4. Sorry, dimension 6, which is the dimension of the stress tensor in 60. Yeah. Go ahead.
Can you motivate a little more why not just work with the super conformal primary trajectories? I understand there are puzzles when you don't, but they contain all the information combined with supersymmetry. So maybe can you motivate a little more why we want to do this?
Yeah. So as you said, if I know this, I know everything, and I know that I should be drawing these trajectories down to spin -3 and everything. And if I know all I need to know, so if I know the full spectrum of A, then I know everything I want about the theory. But the spectrum will have to be such that it's compatible with the demands of the Regge trajectories in all different channels. So if you had the correct spectrum, then it should modulo weird possibilities where the stress tensor sits in some isolated trajectory that doesn't hit, well, maybe not like that, but maybe something horizontal. Or so modulo, the most natural resolution of this puzzle is that it sits in this trajectory. And somehow we're missing information. I know it's very appealing to look at this tiny A and say it has everything, but somehow from there, you wouldn't see these extra constraints. So it was just missing. I don't know why. How do we know we're done? Somehow supersymmetry should have taken care of everything, but it didn't. And there are various other issues like this one in different, with different Regge trajectories in different R symmetry channels. I will focus here just on one issue, which is the stress tensor issue. And the stress tensor, it contributes not only with the stress tensor itself, but it contributes with the scalar, the guy we're looking at as our external operator, and it contributes with the R symmetry current, and they contribute in different channels. And all of these guys are isolated contributions at fixed spin, and they're always within the domain of where we would expect operators to lie in nice Regge trajectories. So then the natural solution of this problem is that we say that the leading long at spin -2 hits this point 2. And if we look at the contribution of the leading long at this dimension, it actually gives exactly, so maybe I zoom out, it gives exactly the same contributions up to this thing here that I'll comment in a minute. But all the others work out if I put here a contribution of -2 over C. So if I fix the OP coefficient of the leading long at spin -2 like this, I add the stress tensor in the leading long trajectory as also happens in bosonic CFTs like this in model. But here the added thing is that it's actually happening at negative spin. There is this weird guy that comes along that shouldn't exist, this scalar of dimension 8. But it turns out this actually cancels another issue that existed, which was a spurious contribution from a chiral algebra short, which gives rise to multiple conformal primary trajectories in this 14 R-symmetry channel. And one of these trajectories again starts at spin 2. And if I continue to spin 0, I get this contribution. And because these are chiral algebra short operators, I actually know their OP coefficients. So I cannot say that this guy would vanish somehow. This guy, there's this spurious contribution to C delta L coming from this. So there is extra unwanted pole in C delta L that does not correspond to a local operator. But it's okay because it actually cancels with this one. It has the right sign. So then our claim is that the leading long trajectory actually extends to L equals -2, where it is, maybe I should say, the light transform of a local operator, and it's the light transform of the stress tensor supermultiplet. And so this leading long trajectory should have a pole at delta equals 2 when L equals -2, and it should have this residue.
Is here L?
Yeah.
Is here L the spin of the superprimary of the long trajectory or some descendant?
This is spin of the superprimary. So it's a superprimary that should have spin. So there's no long there. But then the descendant trajectory comes at spin 2. So maybe if I go back to this plot, it becomes clear. So this is the long superprimary. It starts at spin 0, and it has a descendant that has spin 4. And so a long primary, superprimary of spin -2 would have a descendant of spin.
No, I understand. So I guess in principle, if you were to, I guess it's possible that if you were like to study just these long multiplets and take in the light transforms of these long multiplets, you would see that some, like they become degenerate at the spin -2, and they have another multiplet, can have the stress tensor multiplet inside or something like of the sort.
Yeah, so if you were studying this long trajectory at spin -2, you should find that it actually is, yes, the stress tensor. And I will, so here I was, for the actual superprimary, I was looking below L equals 1. But if you now allow me to go back to the plot, sorry, if I now go back to these Regge trajectories for tiny a that I was drawing, this super function that knows everything, what this expectation would tell you is that this long trajectory should actually be continued such that at spin -2, it hits this point. And it's no accident that I drew it on top of the short trajectory. So they actually coincide, and the two poles are actually such that the two poles cancel at this intersection. So the short and long trajectories meet at L equals -2. And there's actually no residue here. The reason that the short trajectory meet there is that from the chiral algebra to actually, it would be clear that the stress tensor also sits at negative spin in this trajectory. So somehow the stress tensor sits at negative spin in two trajectories that intersect in A. I hope this answers your question, Petr.
Yes, I guess maybe this point that you're raising, that the poles cancel, might actually, yeah, I'm not sure, but it sounds a little bit like it might be a way to see this statement that I think Eric was asking, just from this plot, that it's possible that you could potentially argue that there should actually be no poles at spin -2. Do you think it's a general statement that there are no poles at spin -2 in this C delta J, C delta L?
I wouldn't be able to say for the other trajectories continued. There are other issues, and some resolutions of the issues might involve saying that there are no poles at spin -2. But I think it's just we have no real motivation to argue for one resolution versus another. Okay. But it might be a general feature, yes, from what I'm remembering right now.
All right, thank you.
But yeah, so if you, sorry,
I'm sorry. Please go ahead if you're.
No, I was just going to say for you that so if you had the actual A, then you should find that there is no pole there. But I wouldn't know how to argue from starting from A that there shouldn't be any pole there. So somehow I still need to go back to all the asymmetry channels, even though I didn't want to.
I see, thanks. I was going to ask if we're supposed to be scared when we see two trajectories crossing, as opposed to rejoining, repelling. Should we? Yeah, my understanding was that crossing of trajectories was not a totally settled issue, but I thought that there's kind of some folk bias against taking crossing seriously. What am I supposed to think of that here?
Yeah, so we do have lots of trajectories crossing here, but it's a consequence of supersymmetry. So those we are happy with. This is a funny crossing in the sense that the pole actually vanishes at the crossing. So I don't know. I don't have any reason to say that this shouldn't happen. And somehow it's supersymmetry again that's imposing it, but I don't have any intuition on crossing versus non-crossing here.
I guess I was wondering whether the vanishing of the poles is related to some resolution of that, say some no-go on that kind of crossing where.
Yeah.
It's a good comment, but it's really a question.
Okay. And the other comment I would maybe like to make at this point is that I drew here some schematic as Lavas. This is just some random series that I made up. So these dimensions, of course, can vary along. And in particular, you could set yourself for very large but finite central charge, where all trajectories should basically approach double twists. But if it's large but finite central charge, the stress tensor is there. So this point is kind of pinned down, which means that there's like always a huge anomalous dimension at spin -2, which is a bit weird. Okay, so there are other issues, and we proposed some resolutions, and we also saw how they work out in GFF, but I won't go into those. I just refer you to the paper if you want to see. One quick comment for people who might care is that the trajectories I was drawing here, they're all shadow symmetric. Okay, I was lazy and didn't draw this half, but the idea is that they're all shadow symmetric. And if there's shadow symmetry in A, in tiny a, and then we build the whole conformal primaries in these capital A's that in essence have shifted dimensions and spin, you could wonder, is shadow symmetry guaranteed, or should I go back and check? And this turns out to work spot on. So somehow the superblocks know about shadow symmetry, and even if a trajectory stops being shadow symmetric on its own, there will be another conformal primary that comes to the rescue and makes up the shadow pair of your trajectories. So shadow symmetry just works, and you don't really have to worry about it. Okay, in the last very few minutes.
Yeah.
Madalena,
Yeah.
just the thing about shadow symmetry is also that in principle it leads to some kind of relations between the coefficients of the different conformal blocks in the superconformal block that happen to be obeyed in a the actual superconformal block. But if you didn't know the OB coefficients of the conformal block inside the superconformal block, then shadow symmetry would give you constraints, which is an odd thing to realize. I found it an odd thing that this is true. But sort of analyticity and spin in the shadow symmetry tells you something about OP coefficients of conformal blocks and superconformal blocks. It's an observation that.
Yeah, so what Baldi is saying is that if you didn't know about the superblocks, shadow symmetry would constrain the coefficients that supersymmetry also constrains.
Yes.
Thanks. Okay, so I'm really out of time, so just very quickly on the details of the inversion formula that I left for the end. So this function has a decomposition in 60 blocks. They just happen to be with unequal dimensions. So we can just literally use Caron-Wall's inversion formula after we worry about a couple points. One is that our A is actually not a single valued in Euclidean around 1. We could wonder how important Euclidean single valuedness actually was in the derivation and see what changes. But we just found a quick fix around it, which was to notice that this A, when subtracted to the A of n free tensor multiplets, is actually single valued. And then we can check that the inversion for this series of free tensor multiplets just works fine, and thus we can imagine inverting this subtracted correlator. And then single valued is not an issue. And the other thing is that we need to worry about when the drops can be up, when the arcs can be dropped, which was what gave the condition of L bigger than 1 for Simon's derivation. And so we obtain a Regge bound for all correlator. And this is where this softer Regge behavior that the correlator has is what gave us the condition of L bigger than -3. There's a little star that I should add here is that our proof technically does not work for argument of W equals pi half. So there's one direction in the complex W plane that we haven't bounded, but in all other directions it gives this. And the other region we need to worry about is the second sheet light cone, where I think we can only rigorously bound it like so. And this would only mean L bigger than -1. But if we use the S-channel OP on the second sheet to argue that it goes with the dimension of the lowest twist operator, then we don't spoil this L bigger than -3 condition. So this is the other point I was expecting Slava to be worried about. But this is the same as in the normal derivation, I think. Okay, and then the feature of this A function is that it has a slightly weird crossing equation because it involves not only the crossed A, but it also involves this chiral algebra short correlator. But and then the inversion formula has an usual properties that exact double twists have zero double discontinuity. So the double discontinuity is only 0 from the chiral algebra shorts. You only need to know about the identity and the stress tensor supermultiplet, so the whole multiplet. These non-chiral algebra shorts actually don't contribute at all. They all have zero double discontinuity. And then all longs contribute, as is usually the case. So now we can do this inversion game where we invert what we know and we get out everything from it. And this is So very quickly to end, I'll just flash the results we got. So the idea is that we use as input just the identity and the stress tensor. And then as output comes everything, all the shorts and the longs. And then we take the leading long trajectory and we feed it back in and we invert again and we repeat this iterative procedure a few times. And we can get results for the leading longs and also for these non-chiral algebra shorts. So I'll just show you one plot as an example. This is the dimension of the leading long scalar operator as a function of C, or a power of C, to make the plot more visible. And then what I'm showing here is this line, and everything above it is excluded by the numerics. The numerics are quite old, so they can be improved a lot. This line here would be just a supergravity approximation, and these are the 1/c perturbations of that were computed in these papers, and that we plot here for both AN and DN series. And then here you have the results of our inversion. And the first line is just the first step of the inversion. So if we just invert the chiral algebra shorts, and we see what we get. And then we feed back in and we repeat this iterative procedure a couple times. And this gives you this, at some point it converges and it gives you this line here. That, the results kind of speak for themselves. So it goes closely to the supergravity and the perturbative 1/c results for a while, but then it kind of moves away. And then the last point here is actually the excluded region. And here because we have good numerical data, we actually corrected at each step of the inversion, we corrected this dimension that we could estimate. And this gave rise to this triangle here that is corrected. So this is just really a first exploration of playing with this iterative inversion, of trying to see if we reach a fixed point and if the CFT data corrects itself after you start with an approximate spectrum. And so it's not surprising that for large C, it actually seems to work okay, because for large C's, when anomalous dimensions were small, and so what we were ignoring was not so serious. Okay, so let me move to the end then and summarize. So the plot I was just showing was really the beginning of an exploration of this bootstrapping of the 2,0 series with inversion. We could incorporate better numerics on it, or also consider subleading trajectories, which would be important, or try to distinguish between the A and D series by inputting results from 1/c perturbation theory to try to see if there are two different fixed points that correspond to the different series. And on more general terms, it would also be nice to try to use the structure of the Regge trajectories, like the long at spin -2, and input this into the numerics, because it's something we now know about the long trajectory at a negative spin. Also, the dispersion relations that exist should apply now without subtractions because of a softer behavior, and maybe the convergent sum rules that these people worked out would be interesting to look at for the 60 theory. And although we focus on the 62,0 theory, a lot of the structure remains. So other SCFTs will also have the same interplay between Regge trajectories and supersymmetry. So a lot of what we said would generalize to other series. So I'm sorry for going over time, and I'll stop here. Thank you.
Hi, Madalena. I have a question about this last point, in particular in N=4 spring mills. I mean, a lot is known about this leading Regge trajectory and how it includes the stress tensor. And there you can take, for example, you can take the limit of weak coupling, and you really see this trajectory basically degenerates into, so you have these smooth curves and it degenerates into 3 flat pieces. So in particular, you know that weak coupling, the anomalous dimensions have poles as a function of the spin. So I think this is related to what you were saying, that some anomalous dimensions are also very large at L equals -2 in this picture. So here you also see that yeah, thanks for drawing.
Yeah, this is the type of plot you have in mind, right?
Yeah.
And G changes here in my drawing. That's why I pre-drew all the plots.
So I guess my question is if your analysis matches what was known in the case of n equals 4, and yeah, how the two things compare.
In qualitative terms, yes. So this trajectory that we're drawing is like the single trace leading Regge trajectory. So here my statements were about the fully non-perturbative leading trajectory. So modulo that. I think this fits exactly with what you would expect in n equals 4. The stress tensor should again be a spin -2 continuation of the longs. And I think this fits nicely with all the quantum spectral curve results and so on. Then you were asking about poles when you do perturbation theory in G.
Yeah, I mean, that's a consequence of this corner. I think basically because you have this corner, when you expand in G, you will see poles as you approach that kink of the trajectory. But I guess here in 6D you don't have the analog of this G, so I guess you don't have that.
Yeah, well, we have C, and so something funny also happens if you're, but that's where order by order in 1/C analyticity gets worse, so the spin is pushed up, and so you stop having. So you wouldn't see this there. I don't think you would be able to push to spin -2 by the time the stress tensor appears. And yeah, we didn't look in detail in the n equals 4 results, but qualitatively, I think it looks very similar with the added bonus in n equals 4, you can tune the coupling. If you're working perturbatively in the coupling, I would again worry. So I think in a paper by Simone, you actually show that this is the condition for n equals 4 for the stress tensor. So it really looks similar, and I think again the stress tensor should be the spin -2 operator, which fits with the literature. I don't think I have anything smart to add about tuning the coupling there.
Thank you.
When you do this iterative procedure, when you invert some stuff and then you get the results and plug back, is it automatic that these non-chiral algebra shorts don't get, well, or even, I guess, non-chiral algebra shorts, that they don't get anomalous dimensions?
Yes, it's not obvious, but it happens at first. If you longs and non-chiral algebra shorts don't contribute to the chiral algebra shorts, so they're protected and nothing affects them. And then the second twist, if you go up in twist, the other thing you have are the non-chiral algebra shorts, and these guys, they don't get anomalous dimensions. So they don't get logs in the, if you're looking at the small z expansion. So they just give integer powers of z. It's not obvious, but it kind of follows from the blocks themselves and the double discontinuities. And then anomalous dimensions kick in only for the long dimensions.
So just to clarify, so if you insert some stuff, so you said that first you insert just the identity and stress tensor multiplet, and you apply inversion formula, and so you find some only single poles for this non-chiral algebra shorts, and then and some other stuff, and then you plug it in, but everything back again. You apply inversion formula again, and you again only get single poles for this non-chiral algebra shorts.
Yeah. So the statement is that there is some function times z to the right power for the chiral algebra shorts and the other shorts, and then these are the poles that start to shift. And if you look at small z, these are the ones that come with z log z. So these guys don't get an anomalous dimension.
Well, I understand your I understand your statement that they don't get it, but like, what is the reason for this? Is this some conspiracy of?
It's some conspiracy. So if you take the small z limit of the inversion and the double discontinuity of the long blocks, then this comes out. I don't think I have a better way to state. I don't know if Paul or Shang want to add.
You're unmuted, yeah.
Ah, okay. Yeah, I think that's it. It seems to be some kind of conspiracy that if you add some deep channel block for a generic long multiplet, and you expand it around the S channel limit, where you normally read out the anomalous dimension after taking the d-disk, then indeed you don't get a log for certain powers of z. So these powers of z always give you the same twist and those in S channel. And that means that these twists always come out to be exactly the same. And then starting at a certain twist, I think it's set to the 6th, you get you finally see a log z. And so you get anomalous dimensions for the detail block. But it seems to be a bit of a conspiracy. Like many of these things, they have to work in some way, and it's totally not obvious how it works. But in the end, everything, like you do the computation, and then you say, this is how it works, and then you've seen that. But it's not obvious in advance that this was going to work out in that way.
Yeah, and if I remember correctly, it's only after the d-disk that it actually works like this.
Yeah.
So it's not transparent at all to me.
Okay, thanks.
I have a related question following up. Maybe I don't quite understand, but so when you're doing this iterative procedure, you're summing over some trajectories that you solve for, right?
Yeah, so I was very short on that. We just add the leading trajectory.
Well, so when you obtain these anomalous dimensions, at some point, do you keep iterating with the anomalous dimensions?
Yeah, we iterated a few times with we get the anomalous dimensions and we plug it back in and we iterate. Right. And we corrected for c equals 25 with the numerics and kept correcting.
I see.
But I think Shang can correct me if I'm saying something wrong, but I think it converges rather quick in these iterations to something.
And I guess the main question I want to ask is generically, you might, well, I don't really, well, generically you might add there might be some mixing between trajectories that are nearby. I'm not sure if this happens here in this case. Maybe these trajectories are far apart.
It could happen, and that's one of the reasons we were looking at the leading long.
Okay, I see. Okay, thank you.
Yeah, for subleadings, I think we would have to start worrying about.
So you haven't incorporated subleading?
We haven't incorporated, no, only the leading long.
Okay, thank you.
Can you please show again your plot with the trajectories? With the
which one?
Keep going. That one, thanks. What would you call the leading Regge trajectory?
This is a funny thing, it's reversed. So the leading Regge trajectory here is the chiral algebra shorts. The leading Regge trajectory in the singlet channel is a long trajectory.
But I want a trajectory to hit the y-axis. So what is that trajectory? How do I draw that?
You're asking about the Regge intersect.
Yes, and I'm asking about that crossing point again, I suppose.
I see. Okay, you're asking in this region, I should talk about the leading trajectory being the long. Yeah.
Yes.
And the Regge intersection lies somehow below -3 from this.
This is what I'm asking, how to think about the piecewise nature of these trajectories. Is it really a crossing? What is the right way to think of these in families?
Yeah, in the proper asymmetry singlet channel, then there is no question. It's basically the image of this trajectory here that becomes the leading trajectory. And I guess maybe that's the one I would want to make statements about convexity and so on, because that's the normal 4-point function one. Here it's just what comes out. I'm not sure how to think of the, I mean, yeah, the leading behavior for this function will come first from here and then from there. Yeah, it's a bit of a funny thing.
Can I ask, do you have any thoughts about how to impose this requirement that there's this crossing into the Bootstrap numerics?
No. It's somehow information we have about the trajectory, but it's I wouldn't know how to impose it. It would be interesting to figure out some way to use it, though.
Mm-hmm. Thanks.
Did I understand correctly? You there was this comment about shadow symmetry that then Bolt spoke about for a moment. Is there some possibility of deriving supersymmetry from shadow symmetry and analyticity here? Is that what you were saying?
I don't know if the conditions would be enough, but if you didn't, I guess if you impose the R-symmetry structure, and you're always putting a bit of supersymmetry because you're, yeah, I guess if you impose shadow symmetry in one channel, in the highest SO5R channel, which is the one that gives the A, and then you demand that the others channels have shadow symmetry, it would predict for you some descendants, but we also used here the fact that the descendants are there. So I don't know if you could completely derive supersymmetry. I guess if you didn't know the blocks, it would constrain them. But I guess we made some spectral assumptions. I don't know if Paul wants to add something.
Yeah, I think deriving is too much to ask for. It gives some constraints on the shape of the superconformal blocks. Probably also the dimensions, especially. But there seems to be some kind of reflection symmetry in these, OP coefficients in a superconformal block. It probably is a reflection symmetry that sort of happens if you turn your diamonds on its side, on the other side. You rotate it by 90 degrees, and then it's the it's a reflection symmetry that maps the top to the bottom. And I think if you know the relations in the dimensions in the top half, then shadow symmetry will predict you will tell you the OP coefficients and dimensions in the bottom half.
And maybe also coming back to João's questions, in n equals 4, the same thing applies, and people would actually state, I mean, other people have stated the shadow symmetry of certain channels that looks weird because it's not delta to 4 minus delta, but it's a consequence of shadow symmetry in a different channel.
I was wondering if there's a similar thing going on for, let's say, 3D to 2D non-supersymmetric conformal field theories. So you take a 3D CFT, it has a bunch of Regge trajectories. Now you view the 4-point function in the 3D CFT as a 4-point function in a 2D CFD, which is allowed. It has a nice set of two-dimensional, nice decomposition in 2D conformal blocks. And so you should be able to draw, for every 3-dimensional Regge trajectory, a whole bunch of 2-dimensional Regge trajectories. And the question is, are those Regge trajectories automatically shadow symmetric? Does this give a consistent shadow symmetric picture for the 2D Regge trajectories? And if what we have just derived is any guide, then the answer is it's not entirely trivial, but there's some structure to the decomposition of a 3D block in 2D blocks that ensures shadow symmetry of the Regge trajectories. That would be my conjecture.
If we're comparing the 60 theory to n equals 4, to me the closer analogy is to the n equals 4 theory at the self-dual point of the coupling, where it's inherently strongly coupled, like this theory. Is there anything we can learn about the structure of trajectories in that strongly coupled n equals 4 setting from the way they look here that we didn't think we already knew?
There might be. We haven't done the exercise for the 4D superconformal for n equals 4 in 4D. So one constraint is this of the stress tensor that people have seen. Again, there's this slight difference between the full non-perturbative leading trajectory and the single trace trajectory. But like here, there are probably other issues, other constraints that come from imposing analyticity that you don't see. But we haven't done the actual exercise. So there some sort of non-smoothness in spin that comes very naturally in superblocks, simply because if you have supersymmetry related to different spins, so you often have something like a primary of spin L and a descendant of spin L minus something. And now if you take spin 0, and that gives a L minus 4, the minus 4 block gives a spin 0 block. But this is a very non-analytic in L relation that your blocks have. And now you need to demand that after you do this, the conformal primary Regge trajectories look like smooth functions in L without these discrete corrections. So this type of issues are generic, I think, for low spin in any supersymmetric theory.
I just wanted to make a comment about this picture that's on the slides right now. But the fact that the poles have to cancel at spin -2, I think, well, I'm not 100% sure because I'm not very familiar with this function AZZ bar, but I think that it is possible. So we have an argument that things like this should happen in general. Well, things of similar form should happen. In our paper on light IOP, so we have similar statements when C delta L just has to vanish at some negative spins, provided the Regge intercept is lower. So I think it might be possible to derive it in a similar way. The idea is that if this, if you assume that C delta L doesn't have some vanishing properties at spin -2, and then you try to apply conformal Regge theory to AZZ bar, you'll find that this pulse of or this behavior of C delta L at L minus 2 will contribute in this Regge theory, like with the Regge exponent that's higher than you expect. So here you expect Regge exponent, like the intercept is -3 or below, and yeah, and if you had some stuff at spin -2, then by doing the usual Regge theory analysis, you would pick up this pulse actually as well. And the reason for that is that in the Regge theory, what you do is you have the sum over non-negative spins, so 0, 2, 4, and you write the sum as kind of small contour integrals. So introduce the factor something like 1 over sine pi j, something like this, and you write the sum as small contour integrals around the integer points, around j equals 0, 2, 4, and so on. And then you do a contour deformation of this integral to like a vertical line. But the point is that this factor that you introduced, it will also have pulse at spin -2, spin -4, and so on. And so if you're trying to deform your integral to be at spin -3 to show like this bounded Regge growth, etc., then you will actually pick up the pulse of this factor that you introduced, and they will start contributing. So you have to make sure that you see delta L is vanishing at this other integer values that you want to go past. But yeah, but you have to be, I guess, more careful than this hand waving that I'm doing right now.
Thanks. Yeah, but yeah, I see the point. Yeah, then you would be able to show that actually all these poles have to vanish, which I think will play nicely with some of the other issues that, or some of the other non-eliticities that we listed. Yeah, that's a good argument.
Just to understand the comment of Peter, are you talking about the sphere poles in the Sommerfeld-Watson transform?
Sorry, can you repeat? I couldn't hear.
I was trying to understand your comment. Are you talking about the spurious poles of C delta L in the context of Sommerfeld-Watson transform?
Not spurious poles of C delta L, but about the poles. So in Sommerfeld-Watson transform, we introduce this factor 1 over sine pi pi j over 2 or something like this, so that you actually introduce poles at j equals 0, 2, 4. Yeah, like Madalena is drawing. But the same factor also introduces poles at -2 and so on. But you're not circling this. So there's also going to be a pole from this 1 over sine pi j over 2 at spin j equals -2. But you're not actually circling this pole in your original integral, which was reproducing the sum, right? So when you do the contour deformation, you try to push your contour to j equals -3, you'll pick up this pole. Yeah, exactly.
Right. I see. Thanks.
I guess the chair is somewhere in this room. Any more questions?
I have a question. I was wondering if this procedure works nicely, at least for large C, and maybe even for all C. Could you imagine that you can actually show that this procedure converges, meaning that, okay, here you were just inserting the leading trajectory back, but maybe suppose that you just wanted to be very ambitious and you were inserting everything that procedure was thrown at you. And could you imagine that at least for large C, this somehow converges and gives you an exact cross-symmetric correlator?
That would be very nice. I think we're kind of far from there. So the procedure we did converges to some line, but we should have found actually 2 lines here. So we should have been able to at least find 2 different series, which are these 2 families, AN and DN. So it should have a tiny split. So our procedure was to parse to find this fine difference between the two. So I guess prerequisite to your dream would be to see if you can actually find two fixed points, one corresponding to each theory, that differ a little bit. So even that we haven't done.
But what would happen actually, so if you were to keep everything that this procedure would give you? So why did you not keep everything? Because it would just become very complicated to keep all that stuff. Why did you decide to just retain the leading trajectory for the next step of your transformation?
I think it gets complicated. So even extracting, we're doing the finite Z inversion to extract this leading trajectory. And I think it just gets hard. I mean, getting subleading trajectories, the error in getting that is even harder. There's always an error when you extract this, because we're kind of matching, you need small z to get the poles, but you also need big Z, such that the T-channel expansion you're using is converging better. So I don't know if I would trust our data to keep extracting more trajectories. I don't know if Shang wants to add something here.
Not much. It's just the same as Madalena said. It's basically a technical difficulty of going to higher or subleading trajectories, because we need to subtract the leading powers when we expand in small z, and then the subtraction is just difficult to do if we want to subtract based on already what's an approximate result.
Okay.
Yeah, I think it will be cool to know something more about convergence of this procedure just in theory. I think it would be really cool to have some result there, especially now that we have this seeming ability to find the entire spectrum for all spins, including spin zero. So I think it's cool that in principle, this is a procedure you can do for these supersymmetric theories. But it would be nice to have some theoretical results about the viability of the procedure in theory.
And is this the simplest laboratory? Is the theory to study these questions, or like, for example, okay, supersymmetry was very useful because it allowed you to use this fully convergent, ostensibly inversion formula. But is this the simplest imaginable situation to study this fully convergent inversion formula? Is there something simpler than this, in maybe in supersymmetric theories in lower dimensions?
Yeah, so enough supersymmetry such that you actually get all spins is one, and maximally supersymmetric means you also get these extra constraints, although we could not explore them with this inversion. And I think the other important special thing about 6D is that there's no marginal deformations. So if you want to see if there's some fixed point of this iterative procedure, you better give me a theory that is truly isolated. So n equals 4 supernating mills would have this coupling, and then I don't know what I would expect. But maybe other super conformal series are also neat places to look. Of course, when we started, we were expecting that this procedure would also allow us to look at things below spin zero and check that our solution was reproducing the predicted pole of the leading long at spin -2. But in practical terms, it doesn't work out so nicely or at all. We couldn't extract that pole.
Yeah, we could not reliably estimate. Well, we couldn't. I'm not even sure how reliable all of this is, because it's all extrapolations to finite spin, but it converged to something that made sense. And at spin -2, there was just so much wiggle room and freedom in the procedure that we didn't trust anything we got.
So the way to extract the anomalous dimension when it's large is to use this finite Z inversion technique, but it's some heuristic technique that doesn't have a very rigorous theoretical background. And when the anonymous dimension is too large, for example, for the stress tensor case, it will be -4. And it's way beyond the capability of this finite Z inversion trick.
Any more questions? All right, then let's thank Madalena again.